Let's talk about hydrating an alkene, right? So when you add water to an alkene, the reaction is done in the presence of an acid such as H2SO4, right? Sulfuric acid, which is why the reaction is called acid-catalyzed hydration. The acid is used as a catalyst in the reaction. Now, when you add water to your alkene, right, hydrogen, you're adding hydrogen and OH to the carbons of the carbon-carbon double bond, right? And I think I'm going to make this water blue. And the H2SO4 also blue. Okay. So we're adding H and OH, the carbons of the carbon-carbon double bond, right? And of course, the double bond will break. All your addition reactions, remember, your carbon-carbon double bond breaks. This reaction also follows Markovnikov rule. It follows Markovnikov rule, right? Which states that the hydrogen, which in this case actually comes from the acid, but you'll see that when you watch the video on the mechanism, right? Right now, I'm just teaching you how to quickly get the product, okay? If you're asked for, if you're given a question and you're like, what's the product, okay? If you want to know the mechanism, go to that video, right? Now, the reaction follows Markovnikov rule, which states that the hydrogen will add to the carbons of the carbon-carbon double bond, will add to the carbon of the carbon-carbon double bond with the most hydrogen. But look at the alkene in question, right? Let's number these carbons. 1, 2, 3, 4. Carbon number 2 has only one hydrogen. Carbon 3 only has one hydrogen, right? Looking at the overall alkene, the alkene is a symmetric alkene. So we do not need to worry about Mr. Markovnikov. It's a symmetric alkene. Let me tell you how I know it's a symmetric alkene. Let us circle the carbons of the carbon-carbon double bond, right? Let me go to carbon 3. What's bonded to carbon 3, right? I have a hydrogen and a CH3. So bonded to carbon 3, I have a hydrogen and a CH3. Let's go over to carbon number 2. Bonded to carbon 2, I have a hydrogen and I also have a CH3. So on each carbon of the carbon-carbon double bond, I have the same thing bonded. Carbon 3, and when I say carbons of the carbon-carbon double bond, I'm talking about the two carbons that share the carbon-carbon double bond. Carbon 3 has a hydrogen and a CH3. Okay, the other carbon of the that shares the double bond is carbon 2. It also has a hydrogen and CH3. So this is what we call a symmetric alkene. It's an alkene in which, sorry, it's an alkene in which the carbons of the carbon-carbon double bond has the same two groups. So I have a hydrogen and CH3 on carbon 3. I also have a hydrogen and CH3 on carbon 2. So this makes it symmetric. Whenever you have a symmetric alkene, you do not need to worry about Mr. Markovnikov rule. We don't need to worry about him right now. We will do an asymmetric in a second. So, and the reason for that is because it doesn't matter where I add the hydrogen or the OH, you will get the same product, right? If I put the hydrogen on 2, OH on 3, or I do the reverse, you'll get the same product. If you don't believe me, go ahead and try it out, and you will also see that you get the same alcohol, right, with the OH being on carbon 2. The key here is make sure you name the molecule and number it right, okay? So symmetric doesn't matter because you get the same product. So let's talk about how this reaction will go. I'm going to add my hydrogen and my OH to the carbons of the carbon-carbon double bond, right? So let's draw the carbons here. We didn't lose any of them. Please put them back and let me number them. 1, 2, 3, 4. On carbon 1 here, I have 3 hydrogens. Please put it back because we didn't lose any of them. On carbon 2, I have this hydrogen. I haven't lost it, so I'm going to put it back. Right? On carbon 3, I also still have my hydrogen. On carbon 4, I still have my CH3. Right? Now on carbon 2, I am going to add my hydrogen to carbon 2 and add my OH to carbon number 3, right? This molecule, if we were to name this, we would have to number in the opposite direction so that the hydroxyl group has the lower number. So this would be 2, 4 carbons butanol. And if you don't believe me, go ahead, right, and do the opposite. Add your OH, add the OH to this carbon and add the hydrogen to this carbon and you will end up with 2-butanol. Just make sure you use your IUPAC rules to name. So if the alkene is symmetric, we don't need to worry about mark and you will only get one product, okay? Now what if your alkene is asymmetric? So let's pull up an alkene that is asymmetric. So here's our asymmetric alkene, right? So remember, we're doing the same reaction, and this is what happens in organic. You will get the same reaction. All they're going to do is change the structure. So that's why I always stress. Remember, you memorize, but you don't memorize to put back a definition on a paper. You memorize so you're able to use the concept. Okay? So let's look at what we have here. Let me number our carbons. And let me number the right way. Carbon 1, 2, 3. Carbon number 4. Now, let's look at, we have an alkene, okay? We're adding water in the presence of sulfuric acid. So we're adding a hydrogen and a hydroxyl group. This is water. It's 2H2O, 2 hydrogens, 1 oxygen. Now, let us look at our alkene to see if we need to be concerned about Mr. Markovnikov. All right? Looking at our alkene, let's see if we have a symmetric or asymmetric alkene. Find the carbons that share the double bond. It's carbon 1 and it's carbon 2. I made them red. Next, let us circle the groups on carbon 1. All right? Let us circle the groups that are bonded on carbon 2. Hydrogen, hydrogen is bonded, and all of this is the other group that's bonded. Right? This is a CH2, CH3. So let us ask ourselves the question, is this alkene symmetric or asymmetric? It's asymmetric because the carbon number 1, right, who is one of the carbons of the carbon-carbon double bond, has 2 hydrogens, and I've circled them in blue. Go over here, carbon 2, which is the next carbon that is a part of the carbon-carbon double bond, has a hydrogen and a CH2, CH3, okay? So if you look at blue, I have 2 hydrogens, right? Over here, I don't have 2 hydrogens. I have a hydrogen and an ethyl group, which means that the groups that are bonded to carbon 1 are not the same as the groups that are bonded to carbon 2. So I have myself an asymmetric alkene. So Markovnikov becomes important, right? So let's talk about what happens here. If we look at carbon number 1, so we need to apply Markovnikov rule. So now we need to look at carbon 1 and we need to look at carbon 2 and apply Markovnikov rule. Markovnikov states that the hydrogen, the blue hydrogen that's coming from your acid, will add to the carbon of the carbon-carbon double bond, either carbon 1 or carbon 2, with the most hydrogens on it, or the least substituted carbon. So if you look at carbon 1 has 2 hydrogens directly bonded to it, and it's the atoms that are directly bonded, right? So carbon 1 has two hydrogens directly bonded to it. Carbon number 2 has one hydrogen and then CH2, CH3. Okay? This hydrogen, and these three, they are not bonded to 2. Please do not make that mistake. Okay? Carbon 2 only has one hydrogen directly bonded to it. What's directly bonded here is all of this group. So when we compare carbon 1 to carbon 2 in terms of the number of hydrogens directly bonded to it, carbon 1 for the win. Okay? So when we break the carbon-carbon double bond, so let's draw our four carbons. I did not lose any of them. Please draw them back. So carbon 4, 3, 2, 1. Carbon number 4 still has its three hydrogens. Let's change color. Right? This is carbon 4 with its three hydrogens. Carbon 3 also has its two hydrogens. But let's talk about carbon 2 and carbon number 1. Carbon 2 still has that one hydrogen. I didn't lose it. And carbon number 1 still has its two hydrogens. So let's do Markovnikov. He says that the hydrogen will add to carbon 1, right? That's the carbon of the double bond with the most hydrogen. So let's put the hydrogen on carbon number 1. If you remember your mechanism, right, or just fill in valence, a carbon with three bonds will have a positive charge. From your mechanism, you should realize your OH minus can only add to this carbon. So this is where your OH minus will add. Plus, remember, first thing I told you is that the H and the OH get added to the carbon of the carbon-carbon double bond. To better understand um, why this is adding to 2, I mean, it's the only place it could add though. It's the only carbon of the four carbons here. This is the only carbon with three bonds after I add the hydrogen, which is why I always say all the action takes place at the carbon-carbon double bond. All the action takes place right here. Whatever you're adding is adding here, right? Unless you have a rearrangement of the carbocation, right? That's something else you need to make sure you're aware of. But your OH will add right here. So this reaction, you have an asymmetric alkene, you need to follow Markovnikov rule. If the alkene is symmetric, you don't need to worry about Mark. Just break the double bond and add the hydrogen to whoever you like. Just remember that you can't add the hydrogen and the OH on the same carbon. Cool. Now, let us let us do what chemistry does best and give you an interesting structure so you have something to think about, right? So let's say you have this alkene. Let's say you have this alkene, right? All right. Let's number carbons. 1, 2, 3, 4, 5. On carbon 2 and carbon 3, on carbon 2, I have one hydrogen. And on carbon 3, I have one hydrogen. That's the only number of hydrogens here. I'm not going to put in the rest of the hydrogens because I don't need them for my explanation purpose. But let's talk. We have an alkene now, right? That is asymmetric, right? So the alkene is asymmetric. Let's talk. Let me prove that. Let's talk about that. My carbon, and I like to mix line and structural so you could see both. But remember, people, you must be able to see both, because structures will come in a line or partially structure or full structure, okay? So here, carbon number 2 has a hydrogen and a CH3, right? Carbon 3 has a hydrogen and a CH2, CH3. So my beautiful alkene here is asymmetric. So it's asymmetric, right? And I'm adding water, right? We're adding H2O in the presence of sulfuric acid. Okay, so we're adding water in the presence of sulfuric acid. But look at this now. The alkene is asymmetric, but the number of hydrogens on each one of these carbons is just one. So you're like, okay, what do you want me to do? Listen, in a situation like this, and I'm going to tell you what happens. But let's say you showed up in an exam and you got this, and you didn't know what to do. People, it's simple. Play around with the structure. Add a hydrogen to carbon two for one product and add your OH to carbon 3. Then do the reverse and see if the two products are the same. Because once you have a molecule that is asymmetric and you have the same number of hydrogens on the carbons of the carbon-carbon double bond, the probability of you adding the hydrogen here is the same percentage as the probability of you adding the hydrogen right here, right? This reaction actually gives you two products, and I'll give you something to memorize once we've established it. So let's look at it, right? We are going to, for the first product, this is what we're going to do. We're going to add to carbon 1 the hydrogen, not carbon 1, I'm sorry, double bond is between 2 and 3. We're going to add to carbon number 2, I am going to add the hydrogen. To carbon number 3, I am going to add the OH. Remember, that's all we're adding. Everything is happening right here. Okay? So let's do that and get our first product. So we have 5 carbons. Let me see. So let's number them. 5, 4, 3, 2, 1. All right? On carbon 2, I am adding my hydrogen. I'm following this, right? On carbon 3, I am adding my OH. Remember, the double bond breaks, yes? And you add the hydrogen and the OH, the carbons of the carbon-carbon double bond. That's all I've done, right? So this is one product, yes? Let us do the opposite and see what happens. Let us add to carbon 2, we're going to add the OH, and to carbon 3, we're going to add the H. Oops. Carbon 5, 4, 3, 2, 1. On carbon 2, we're adding OH. On carbon 3, I'm adding H. Now look, let us look at this and look at this and see they're not the same molecule, right? This right here has your OH on carbon 3. So this is 3-pentanol. If you ever want to know if two things are the same, name it, right? Plus, you should be a pro on isomers by now. Let's also, if we name this, it's 2-pentanol. So let me tell you something now, all right? If you get an alkene, right, where you have the same number of hydrogens on the carbons of the double bond, right, and the molecule is asymmetric, or if you want to look at it, let me give you something easier than asymmetric. If you have a molecule, an alkene, where the hydrogen, number of hydrogens on the carbons of the carbon-carbon double bond is the same, they both add 1, and you have an odd number of carbons in that long chain, you are going to get two products. If you don't believe me, come up with a compound. You can do one with 7 and see if the two products are going to be different. If you think about it too, if you add, let's say in my first situation, I add the OH to this carbon, right? You should realize that if I added the OH to the next carbon on the other go round, this carbon, if I number from this direction, is not still 2, so the names would be different. Either way, just remember, same number of hydrogens on the carbon in a molecule that is not symmetric, it's asymmetric, you will get two products once the number of carbons here is odd. If you don't remember any of that, you're in an exam and you're like, lady, I don't remember any of what you just said. Just perform the reaction. Add the hydrogen to 2, add the OH to 3, right? Do the opposite right? As in flip it. And if you name the two compounds and they are different, then you know you get two products. That's also an easy way to remember. So for alkene reactions, look out for symmetric, asymmetric, and if it's asymmetric with the same number of hydrogens. Remember the reaction follow Markovnikov rule. Don't complicate it. You're breaking the double bond, adding hydrogen and OH. And just remember the guy's rule.